This video lecture addresses image acquisition in remote sensing with a focus on thermal imagery. There are three important properties to consider for electromagnetic energy. First, the wavelength is represented as the distance from one wave crest to the next. Second, the frequency is measured as the number of crests passing a fixed point in a given time period. Third, the amplitude is the height of each peak. While most students of remote sensing are familiar with visible spectrum ranging from roughly 0.4 to 0.7 micrometers, it is important to consider the other portions of the electromagnetic spectrum beyond what the human eye can detect. Our specific focus in this lecture is on the range beyond the visible spectrum in the near and mid-infrared and the thermal infrared. Some other portions of the spectrum used in remote sensing include the ultraviolet and microwave regions of the electromagnetic spectrum. In general, the infrared radiation is sometimes called, quote, below the red, because frequencies are lower than the red portion of the visible spectrum. The infrared portion of the electromagnetic spectrum was discovered in 1800 by British astronomer Sir William Herschel. Then, in 1847, two Frenchmen, A.H.L. Fizeau and J.B.L. Foucault, demonstrated how the optical properties of infrared are similar to those of visible light. The use of infrared in remote sensing focused on emissive infrared or thermal infrared, with radiation from approximately 7 to 18 micrometers. In practice, what we call far infrared has overlap with passive remote sensing of microwave radiation. In some applications, absorption by atmospheric particles restricts use. Thermal infrared remote sensing collects information on surface temperatures and thermal properties of soils, rocks, vegetation, and man-made structures. Detectors are devices formed of substances known to respond to energy over a defined wavelength interval. The detector generates weak electric signal, and the strength of the signal is related to the radiances in the field of view of the sensor. An example of uncommon materials that are used in the thermal detectors are indium antimonide and mercury-doped germanium, with peak sensitivity near 10 micrometers in the far infrared portion of the spectrum. Another example of a material used in a detector is mercury-cadmium telluride, which is sensitive over the range of 8 to 14 micrometers. Detectors are cooled to very low temperatures, approximately -200°C, for maximum sensitivity. As Natural Resources Canada, 2014 paragraph 1 explains, quote, many multispectral MSS systems sense radiation in the thermal infrared as well as the visible and reflected infrared portions of the spectrum. However, remote sensing of energy emitted from the Earth's surface in the thermal infrared 3 micrometers to 15 micrometers is different than the sensing of reflected energy. Thermal sensors use photodetectors sensitive to the direct contact of photons on their surface to detect emitted thermal radiation. The detectors are cooled to temperatures close to absolute zero in order to limit their own thermal emissions. Thermal sensors essentially measure the surface temperature and thermal properties of targets. End quote. Thermal detectors with coarse radiometric resolution have low sensitivity so that only differences in brightness are recorded and most finer detail in a scene is lost. In contrast, thermal detectors with fine radiometric resolution have high sensitivity and finer differences in scene brightness are recorded. You may have heard of the concept of signal-to-noise ratio, often written as SNR or S divided by N ratio, as the measure of signal strength to the background noise. In sound communications, the SNR is generally measured in decibels. In remote sensing, we talk about the signal as the differences in image brightness caused by actual variations in scene brightness, and the noise as variations in brightness unrelated to scene brightness, for example, due to system performance or as a contribution from a sensor. Thermal scanners are the most widely used imaging sensors for remote sensing. These scanners sense radiance of features beneath an aircraft flight path and in turn produce images of terrain. There are two main types of thermal sensors. First, the object plane scanners, which view the landscape by means of a moving mirror. Second, the image plane scanners, which have a wider field of view for a more comprehensive image of the landscape. Thermal scanners are used across many fields and for many applications. Thermal radiation is emitted by all objects at temperatures greater than absolute zero, but the intensity and peak wavelength vary with object temperature. The immediate source of emitted thermal radiation is shortwave solar energy, with exceptions in geothermal energy, man-made thermal sources, and range and forest fires. Short, no date, notes, quote, remote sensors that cover two thermal intervals, the 3 to 5 micrometers and the 8 to 14 micrometers, broad bands corresponding to 2 atmospheric windows, allowing sensing of thermal emissions from the land, water, ice, and the atmosphere, have been flown on airplanes for several decades. Here are temperature variations in Mount Hope Bay and part of Narragansett Bay, Rhode Island, made from an aircraft survey. End quote. In this image, the warmer colors, for example oranges and reds, represent warmer temperatures, and the cooler colors, for example greens and blues, represent cooler temperatures. Emissivity equals the radiant emittance of an object in relation to emittance of a black body at the same temperature. This slide offers a few emissivity coefficients of common materials. In applications like remote sensing, keep in mind that a thermal scanner may detect radiation that is reflected from the surface of the object, that is emitted by the object, and that may be transmitted through the object. Thermal remote sensing may be captured from plane or space-based sensors. As short no-date notes, quote, thermal imaging has been done from various space systems, many of the meteorological satellites, including at least one thermal channel. These include most geostationary satellites. This is a map of thermal variations off the east coast of the U.S. made from meteorological data. End quote. The following references were used in developing this video lecture.